Reservations in two-way slabs by means of yield lines. This video deals with the case 21 to 25, and it's about a concrete slab with fixed end supports on the four sides. It will handle case 25, which is the case, a more general case with a rectangular reservation in the slab, and it's calculated by the method of subtracting yield lines. Consider a rectangular slab with a reservation in it, D1 over D2, and the position is D3, D4, D5, and D6. We use the method of subtracting yield lines, just the corner of the reservation will go to the axis to where the axis of rotation crosses, independent of the angle. So that's how we can draw the four yield lines. We must take care of this method because when D3, for instance, is too small, then the yield line is not realistic. Or when D6 is too small, or D5 or D4. It's only when D3, 4, 5, and 6 have a reasonable dimension. The conditions, it's a two-way slab, so B is between A and 2A. The maximum hole diameter or reservation diameter is, of course, D2 must be smaller than B, and D1 must be smaller than A. And the position, well, the position is only the sum of those, D1, D3, D5 must be A, and the sum of D4, D2, and D6 must be B. Now let's investigate what type of hole can be made with this case 25, and you will see that we have different shapes or positions of the rectangular reservation. It can go all over the slab. We calculate the work done by the external forces, and we start with the green areas, which is the summation of the triangles. And it is, of course, D4 times D3, D6 times D3, and so on. It's just the surface of the green area, and the mean deflection is delta over 3 because of the triangle. And then we add up the orange areas indicated here, which consists out of rectangulars. The mean deflection is delta over 2, and then we take a total surface of it. So, for instance, this is D3 times D2, or D4 times D1, and so on. The work done by the internal forces are the bending moment, the yield line, M times B divided by D3. So delta over D3 is the mean angle of rotation. For here, it's A divided by D6. This is B divided by D5. And this is A divided by D4. And then the other elements in the corners, it's always the same. It's this yield line projected to the north. It's still D4 divided by, multiplied by delta over D3. And corrected on the other side, it is D3 divided by D4. And so for each corner, we do the same and we arrive at this formulation. Cannot write it out in one formula. You can do it, but it's a very large formula and not very practical. So we leave it like it is there. The bending moment is then given by E is equal to D, and then you have Q times AX divided by DX. And the EX is E over Q delta, and DX is equal to D over M delta. The bearing capacity is then defined at 100 times M0 divided by M. M0 is the maximum bending moment without the reservation. And we work with dimensionless parameters. So for case 25, the conditions are then that alpha 1, alpha 3, and alpha 4 are equal to 1, and alpha 2, alpha 4, and alpha 6 are equal to alpha. Let's just give an example how we can handle this. We have a slab 9 by 6 meters with a depth of 200 millimeters and a concrete cover of 40 millimeters with a floor finish of 1 kilonewton per square meter and a live load of 20 kilonewtons per square meter. What is the reinforcement needed when we make a reservation as indicated on the drawing? We start with calculating the load in ULS, which is 1.35 times the permanent load plus 1.5 times the mobile load and gives you 38.1 kilonewton per square meter. We fill in the different, or we substitute the different values of the parameters, and we use the formulas of the previous slide, and you find that M is 36.9 kilonewton meter per meter. We convert this into reinforcement. To do this, we need the lever arm in X direction, the lever arm in Y direction. We take the mean lever arm, which is 148 millimeters, and the needed reinforcement is then 1.1 times the maximum bending moment divided by the lever arm and the yield strength of the reinforcement. And you will need 700 square millimeters per meter, or it's a diameter 12 every 150. Or you can go for a lower diameter, then you fill in there 10, you have a different lever arm, and you can also use diameter 10 every 110. So, but preferably you should take diameter 12 every 150 millimeters. Now let's see what we can do with those type of formulas. We can make a study of reservation in a slab and see what are the different possibilities of making a reservation. For instance, we got a reservation like this in a slab of 9 by 6 meters, where D4, so it's a reservation in the middle of the slab, and it can go from the left-hand side, which is 1.2 meter, up to 7.2 meter on the right-hand side. So this is a type of reservation that we are going to study just as an example to see what is the influence on the position. What is the influence of the position of the reservation on the bearing capacity of the slab? The reservation itself is 1.2 by 1.2 meter. So because this is in the middle of the slab, that means that D3 is 2.4 and D4 here, this D4 is our parameter and it's alpha 4 times A. So D6 is automatically because from the formula, because B equals D2 plus D4 plus V6. So you have 7.8 minus alpha 4 and D5 is 2.4. So this is the same, D4 or alpha 4 is just divided by 6. So now we'll see what are the formulas, what do they tell us? We calculate the work done by the external forces, and when we substitute all those different parameters, we find it's 21.78 square meters. So it's not a function of alpha 4, so it's a fixed. The work done by the internal forces, we substitute and we see that it is a function of alpha 4, and it looks like this. Then we say B is equal to E, we get M from it, and M equals then this equation. M0, we've seen that in the previous slides or videos, it's equal to this formula. When we fill in alpha, which is 9 divided by 6, fill in alpha, then we got M0 is this, and 21Q divided by 20. So we can calculate the bearing capacity, which is 100 times M0 divided by M. And this is the formula in function of alpha 4, which is the horizontal position. We can make it a graph where x is alpha 4 from 0.2 to 1.1, and the y-axis is the bearing capacity, and the bearing capacity on the left-hand side, 0.2, is this position. It's 129. The extreme value here is at 0.65, so it's almost in the middle. Gives you 102. And on the right-hand side, it's this point and gives you 129. You'll see that for this reservation, going from left to right, there is no problem concerning bearing capacity because everything is above 100%. Now we've seen two ways of choosing the yield lines, calculating the yield lines. The first one is the 30, 45, 60 rule, and the second one is vectoring yield lines. So what would we choose now? So I'll give you an example of two identical cases, and the first one, we draw the yield lines by the 30, 45, 60 rule. So it means that because this is fixed support, that this is 45 degrees. Everything is 45 degrees. It comes here, and then there is the reservation. Or we use attracting yield lines. It means the corner attracts the yield line, like that. It gives a realistic view of yield lines. So which one could we choose? Well, we calculate the bearing capacity according to this method. It's 106, or M is equal to 0.988Q. And for attracting yield lines, the bearing capacity is 119, or M is 0.885Q. So this means that attracting yield lines, to use this method, it gives you more capacity. So it's a little bit unsafe to do it. It's very easy, that's for sure. It's very easy, and sometimes it's the right choice because it's a very realistic yield line pattern. But I recommend to use the 30, 45, 60 rule in as many cases as you can.